We're pleased to have Andrei Rapinchuk coming from the University of Virginia, who will speak about, with a title, Towards the Eigenvalue Rigidity of Zariski-dense Subgroups.
Thank you very much. It's a huge honor for me to speak in this conference. There will be several themes in my talk. First, I would like to report on a joint work with Gopal Prasad on isospectral and length-commensurable locally symmetric spaces. I will then discuss the problems in the theory of algebraic groups that this work has led to. These problems have to do with characterizing algebraic groups having the same isomorphism classes of maximal tori, and in particular division algebras having the same isomorphism classes of maximal subfields. Now, these results and also relevant conjectures point to a new form of rigidity, which we coined eigenvalue rigidity. And I would like to begin by explaining what we mean by this. Now, by rigidity in the classical sense, we mean statements of the following type. Now, suppose we have two semi-simple Lie groups, G1 and G2, and each of them will have a large subgroup. It could be an arithmetic group, or S-arithmetic group, or a lattice, or a commensurate of a lattice. The point is that under appropriate assumptions, a homomorphism or isomorphism between these subgroups can be extended, or at least virtually extended, to a homomorphism of the ambient Lie groups, as shown in the following diagram. Of course, there are many variations, and I will not give you precise statements. What I want to point out, though, is the following consequence. For simplicity, let's take our first group to be just SL and Z. And let the second group be the group of points of some absolutely almost simple algebraic group over the ring of integers in some number field. Then, if gamma 1 and gamma 2 happen to be isomorphic or even virtually isomorphic, we can say that the field K must in fact be Q, and the ambient group must be isomorphic to SLN over Q. So in other words, the structure of a higher rank lattice or an arithmetic group determines two things: the field of definition and the ambient algebraic group as a group over that field. However, if we try to obtain something similar for general Zariski-dense subgroups of algebraic groups, we run into a problem, which is that general Zariski-dense subgroups may very well be free groups. In fact, there is a famous theorem of Tits that says that the group of rational points of any semi-simple group over a field which is not an algebraic extension of a finite field always contains a Zariski-dense free subgroup. So in this case, this free subgroup has no structural imprint of the ambient algebraic group, and there is no way you can recover any essential data from that Zariski-dense subgroup. However, our work indicates that one should be able to recover such data as the field of definition and the ambient algebraic group actually from any Zariski-dense subgroup, if instead of structural information we use very minimal information about the eigenvalues of the elements of that subgroup. And this is really one aspect of what we mean by the eigenvalue rigidity. There are some other aspects, and I would like to refer you to my article. But before I show you any results, I would like to discuss the following two issues. First of all, how do we match the eigenvalues of elements of two Zariski-dense subgroups? To say the least, the elements can be represented by matrices of different sizes. They will have a different number of eigenvalues. And the second issue is, why do we care about the eigenvalues of elements of the Zariski-dense subgroups? In fact, in his beautiful talk, Emmanuel Broyard already gave a reason for that. So I will give you yet another reason for that, which will be different from his. Now, the first of those questions brings us to the notion of weak commensurability. So let F be a field of characteristic 0, and suppose we have two matrices, gamma 1 and gamma 2 over F of sizes n1 and n2 respectively. Let us assume that these matrices are diagonalizable, and let lambda 1 through lambda n1 and mu 1 through mu n2 be their eigenvalues in a fixed algebraic closure. We say that these two matrices are weakly commensurable if there exist integers such that the following condition holds. What it means is that some non-trivial multiplicative combination of the eigenvalues of the first guy equals some multiplicative combination of the eigenvalues of the second guy. Furthermore, well, suppose we have two algebraic groups, G1 and G2, and in each of them we're given a Zariski-dense subgroup. We say that our subgroups, gamma 1 and gamma 2, are weakly commensurable if every semi-simple element gamma 1 in gamma 1 of infinite order is weakly commensurable to some semi-simple element gamma 2 in the other group of infinite order, and vice versa. Now, this condition can be restated in several equivalent ways, one of which is the following. So, semi-simple elements gamma 1 and gamma 2 in the respective algebraic groups are weakly commensurable, even only if there exists rational representations of those groups such that the images have just one non-trivial eigenvalue in common. You cannot really demand less than that, just one non-trivial eigenvalue. Now, this tells us about one thing, namely that weak commensurability is actually independent of the choice of the matrix realizations of G1 and G2. Another remark is that weak commensurability tends to be really inconsequential for individual matrices. You can easily write down matrices that are weakly commensurable, but which are not conjugate, and neither are their powers. But this property turns out to have quite remarkable consequence for the Zariski-dense, and particularly for arithmetic groups, as we will see later in this talk. Now, let me tell you why we introduced this notion. Our motivation came from geometry. So suppose M is a Riemannian manifold. In differential geometry, one attaches to M different sets of data. For example, the Laplace spectrum. Now, when we talk about the Laplace spectrum, we usually tacitly assume that our manifold is compact, in which case it's just the eigenvalues with multiplicities. Another useful set of data is the so-called length spectrum, which is the collection of lengths of closed geodesics occurring in this space. Let me also recall that two Riemannian manifolds, M1 and M2, are called commensurable if they have a common finite sheeted cover, where the maps are, of course, local isometries. And then one asks the following question. Suppose we have two such things, M1 and M2. Are they necessarily isometric or commensurable if they have the same Laplace spectrum, in which case they are called isospectral? Or they have the same length spectrum, in which case they are called isolength spectral? Or they satisfy the following condition, which we call length commensurability. What it says is that the set of rational multiples of the lengths of closed geodesics occurring in the first manifold coincides with the set of rational multiples of the lengths of closed geodesics we have in the other manifold. Well, among these questions, question 1 is probably most famous. It's best known in its informal formulation given by Mark Katz. Can you hear the shape of a drum? Let me start with the bad news. There exist examples of isospectral and isolength spectral manifolds that are not isometric. In fact, there are two famous constructions of counterexamples in the class of local symmetric spaces that were proposed by Vinira and Sunada. So the construction of Vinira used some delicate properties of quaternion algebras, arithmetic properties, I should say, while the construction of sonada was based basically on group theory, and it was more general. It basically kills any hope to prove that isospectral should imply isometric without any additional assumptions. However, by their nature, both constructions produce commensurable manifolds. So probably we're asking simply the wrong question. Maybe we should ask about commensurability instead of isometricity. Still, there are examples of non-commensurable isospectral manifolds. But in fact, one expects to prove the commensurability of isospectral manifolds in many situations. Now, prior to our work with Plassat, this was done only for arithmetically defined Riemann surfaces and hyperbolic 3 manifolds. Now, in our work, we were able to prove, indeed, the commensurability of many arithmetically defined locally symmetric spaces. And the critical point was precisely connecting the geometric condition of isolength and the analytic condition of isospectral to this algebraic condition of weak commensurability. Now I would like to make this more precise, for which I will need to introduce some additional notations. So let G be an absolutely simple real algebraic group. Let G script be the group of real points, considered as a Lie group. Now we pick a maximal compact subgroup and look at the quotient, which is precisely the symmetric space associated with the situation. Now, given a discrete torsion-free subgroup of G script, we can mod out on the other side, and the resulting thing is called the locally symmetric space. The class of locally symmetric space is pretty broad. For example, it includes all Riemann surfaces of genus greater than, and also many other things, hyperbolic manifolds and so on. Now, we say that X sub gamma is arithmetically defined if the subgroup gamma is arithmetic. Now, in this more specialized situation, I would like to make some additional comments about our conditions 1, 2, and 3. One important thing is that condition 1, isospectrality, in fact implies condition 2. That is, isolength spectrality. The proof is highly non-trivial. It uses the trace problem. Another remark is the following. Remember we said that maybe we should modify the original question. Maybe we should ask about commensurability. Okay? But then the point is that the sets E and L that were used to define those conditions are not invariant under passing to a commensurable manifold. So the conditions 1 and 2 themselves are not invariant. So to fix the situation, we introduce the condition of length commensurability, which I already introduced. It says that the set of rational multiples of the lengths of closed geodesics in the first manifold equal the set of rational multiples of the set of closed geodesics in the other manifold. Now, this set of rational multiples is nowadays called the rational length spectrum. So it has certain advantages. First of all, it is invariant under passing to a commensurable manifold, which makes condition 3 invariant under passing to a commensurable manifold. And also, in certain situations, the rational length spectrum is a more tractable thing than the length spectrum or the Laplace spectrum. So, if we have a compact locally symmetric space, that condition 1, isospectrality, implies condition 2, isolength spectrality, which in turn implies, of course, condition 3, which is length commensurability. But the point is that now condition 3 can be tied to our algebraic condition of weak commensurability. Namely, we have the following theorem. So suppose we have two algebraic groups, and for each of them we consider some locally symmetric space. So we have two locally symmetric spaces. Now the assumption is that these locally symmetric spaces are of finite volume. Now in this situation, the length commensurability of the spaces implies the weak commensurability of the corresponding fundamental groups. Of course, it's not surprising that we have some condition on the eigenvalues because the length of closed geodesics can be expressed in terms of values. But they're expressed as the logarithms of certain eigenvalues. And that equation is not easy to analyze. So actually to sort things out, we need to use certain results and conjectures from transcendental numbers. Okay? Now, to prove that in fact our local symmetric spaces are commensurable, what we need to prove is that the corresponding fundamental groups, gamma 1 and gamma 2, are commensurable up to an isomorphism between G1 and G2, which means that they become commensurable in the usual sense, the intersection has finite index in both, after applying a certain isomorphism to one of them. So, for geometric applications, we need to answer the following question. When does the weak commensurability of gamma 1 and gamma 2 imply their commensurability? And as we will see later, so this is indeed the case for many arithmetic groups, but an interesting thing is that weak commensurability has in fact strong consequences for arbitrary Zariski-dense subgroups. And this is what I'm going to talk about next. So let's fix some notations. So let F be a field of characteristic 0. G1 and G2 be absolutely almost simple algebraic F groups. And suppose that in each group we are given a finitely generated Zariski-dense subgroup. Then the first result says that if gamma 1 and gamma 2 are weakly commensurable, then either G1 and G2 have the same type, or one of them is of type Bn, the other is of type Cn. And in fact, the second case can in fact be realized. We'll see a result of this effect. And already this result is quite interesting because, like I said, in principle, gamma 1 and gamma 2 can very well be free groups, which means that you cannot recover any information. But somehow, by looking at the eigenvalues, you can recover the type. Now, of course, what we prove here is that G1 and G2 have the same order of the Weil group. And it's an experimental fact that the order of the Weil group distinguishes the type, except for this ambiguity between B and C. Now, to formulate the second result, I need one additional notation. So, for a Zariski-dense subgroup, we'll let K sub gamma denote the field generated by the traces of elements of gamma in the adjoint representation. It's a so-called trace field. Its significance is that there is a theorem of Windberg that says that K sub gamma is the minimal field of definition of the adjoint of gamma, which means that there is a basis in the Lie algebra such that all transformations at gamma can be represented by matrices with entries in K. And K is really the minimal field with this property. To take this one step further, so let's consider the so-called algebraic hull, which is simply the Zariski closure of at gamma in the corresponding GL. So it follows from Windberg's theorem that G is a K-defined algebraic group. In fact, it's an FK form of the corresponding adjoint group. In other words, it becomes isomorphic to the original group G bar after the base change from K to F. Now, in fact, this thing, G script, is an important characteristic of gamma. When gamma is arithmetic, it in fact determines gamma up to commensurability. And this is how we really analyze arithmetic groups in that work. We try to say something about the algebraic hull. So if we can identify the algebraic hulls, we can say that our groups are actually commensurable. Okay. Now, here's our second result. If gamma 1 and gamma 2 are weakly commensurable, then they have the same trace field. And I should probably emphasize that here the fields are actually equal. So if we use structural rigidity, we can only say that the fields are isomorphic. Now here, the fields are actually equal at the subsets of F. So now let me recap what we just said. So a class of weakly commensurable groups basically determines the type, except for that little ambiguity between Bn and Cn, which means that it determines the group, the ambient algebraic group over the algebraic closure. It also determines the field of definition. So the next natural question would be to ask if it determines the algebraic hull as a group over that field of definition. Unfortunately, this is not the case, even for arithmetic groups. But as a replacement, we would like to propose the following finiteness conjecture. Well, it's a bit technical, so let me first state it, and then I will tell you what it actually means. Again, in our standard setup, suppose we have two absolutely simple algebraic groups over a field of characteristic 0. Now, and suppose we are given a finitely generated Zariski-dense subgroup in the first group. And we let K denote its trace field. Then we expect that there should exist a finite collection of K forms of the other group such that if gamma 2 is a finitely generated Zariski-dense subgroup in the second group, which is weakly commensurable to gamma 1, then it can be conjugated with the group of rational points in one of those selected forms. In fact, in some cases, we expect this R, the number of forms, to be 1, which means that the form is completely determined by the weak commensurable subgroup. So what it basically says is that if you give me one Zariski-dense subgroups, then weakly commensurable Zariski-dense subgroups can exist in only finitely many forms of the second group. For example, let's take a central simple K algebra. Then SL1A is used to determine the algebraic group defined by elements of reduced norm 1, and let's consider the corresponding adjoint group. Now, fix a Zariski-dense subgroup in the group of K rational points and assume that the corresponding trace field, well, I'm sorry, the corresponding trace field is in fact K. Then the finiteness conjecture would give us the following. Then we could say that there are only finitely many central simple algebras such that the corresponding algebraic group can contain a Zariski-dense subgroup which is weakly commensurable to our first group. Which means that this Zariski-dense subgroup, no matter how small it is, it can be small, determines the ambient algebraic group up to finitely many possibilities. And we have similar interpretations, of course, for orthogonal groups of quadratic forms and so on. Now, the finiteness conjecture, as I stated it, is known only in the following cases. First, when the base field is a number field, although the subgroup doesn't have to be arithmetic. And the second case is when G1 is an inner form of type AL. In other words, the group associated with some simple algebra. So the thing that I had on the previous slide, this consequence is already a theorem. Well, the thing is that these two cases actually cover all lattices in real semi-simple groups. So we know the finiteness conjecture for all lattices. Now, the general case is work in progress at this point. So remember, we dealt here with arbitrary Zariski-dense subgroups, but we have much more precise results for arithmetic and S-arithmetic subgroups. I packaged them in two theorems. This theorem is joint work with Gopal Prasad. Again, suppose we have two absolutely almost simple algebraic F groups. Again, let's keep the assumption that F is of characteristic 0. And now suppose that in each group we have a certain Zariski-dense S-arithmetic subgroup, where S, of course, refers to certain set of places of the field of definition. So, now, Assume now that G1 and G2 are of the same type, which is different of the following three types: AN, DN plus 1, and E6. Then, if the subgroups are weakly commensurable, then they are in fact commensurable. So if we exclude these three types, then weak commensurability indeed implies commensurability. Now let me make some additional comments. One is that a little bit of a surprise for us here was that the type D2n behaves differently from the type D2n plus 1. In fact, the case of type D4 here was handled for us by Skip Garibaldi. Now, next, for experts in Lie groups, these are precisely the types where -1 is not in the while group. And also these three types are honest exceptions. Using the fact that -1 is not in the while group, so we produce examples of groups which are weakly commensurable but not commensurable. Okay.
You say the same type, so they, a priori there can be some BR and BS with RS different, for instance.
No, this cannot happen.
Sorry?
This cannot happen. So
yeah, but so the theorem is, even if you do that, because it cannot happen, you can say it's okay.
Right. We will see the second theorem, which treats the case where one group is of type Bn, the other is of type Cn. So yes, thank you for that remark. So in fact, this case 1 plus this theorem we'll see on the second slide will cover all possibilities. Thank you. Where was I? Yes. So now what happens in the remaining types? Like I said, in the remaining types we have counterexamples. But at the same time we have the following finiteness theorem. So if we fix one as arithmetic subgroup and look at all others that are weakly commensurable to it, there are only finitely many up to commensurability. This applies to all types. Of course, this is very much consistent with the finiteness conjecture, but it's a more precise result. So remember, in the finiteness conjecture, we talk only about the algebraic hull of the group. Okay. Here, because our groups are assumed to be S-arithmetic, we can actually say that they are commensurable. Next thing, you may remember that I defined weak commensurability using only semi-simple elements. In fact, it turns out that weak commensurability can see the presence of non-trivial unipotents. So if the groups are weakly commensurable, then one has non-trivial unipotents, even only if the other one does. And one more result is what we call the arithmeticity theorem. So if we have an S-arithmetic lattice, and we have another lattice which is weakly commensurable, then it also has to be S-arithmetic. Okay. As Professor Ravat mentioned, so this theorem basically treats the case where both groups are the same type, but we had also another possibility that one group is of type Bn, the other group is of type Cn. And in a joint work with Skip Garibaldi, we prove the theorem that tells us when such things are in fact weakly commensurable. So now suppose G1 is of type Bn, G2 is of type Cn, and again in each group we have a Zariski-dense S-arithmetic subgroup. What we need is the algebraic hull of the subgroups. We denote this by G script I. Now what we proved was that these groups are weakly commensurable if and only if the algebraic hulls, as we say, are twins, which means the following. They are both split over every non-Archimedean place of K. And they are either split or isotropic over each Archimedean place. So, of course, the degenerate case in this situation is when our groups split over all completions. And then we get for free that, then, of course, our groups are weakly commensurable. So it is possible to have groups in type Bn and type Cn, which are weakly commensurable. And this tells us precisely when this can happen. Again, I don't expect you to remember all these statements, but so I want to convey the feeling that we pretty much know everything about weak commensurability of as arithmetic groups. And now I would like to switch gears and tell you about some geometric applications of these results. So in the same situation as before, so we have two algebraic groups, G1 and G2, and to each of them we attach a certain local arithmetic space. Now the assumption is that both spaces are of finite volume, and moreover, one of the spaces should be arithmetic. Okay. If these spaces are length commensurable, then the other space is also arithmetically defined. So somehow the length of closed geodesic can see if your space is defined using an arithmetic subgroup. And the second is really my personal favorite. So it turns out that one space is compact even only if the other space is compact. Now there is no purely geometric explanation of this phenomenon. And we don't know if it still holds if we drop the assumption of arithmeticity. But what tends to happen in the arithmetic case is that a non-compact guy has more lengths of closed geodesics than the compact guy, which of course makes sense, but there is no geometric explanation. And then, as before, we have a certain finiteness result. Now fix one space, x gamma 1, and look at all other local arithmetic spaces that are length commensurable to the first one. Then it consists only of finitely many commensurability classes. In fact, you have a single class if you exclude these three bad types.
You have counterexamples in those cases?
For length commensurability, yes. But for isospectrality, no.
Sorry?
I'll get to this. Yes, these are honest exceptions. You can construct length commensurable, but not commensurable. Thank you. This is so-called, in some sense, the mother theorem, so we can interpret it in some concrete geometric situation. So let me show you what happens for arithmetically defined hyperbolic manifolds. Okay. In fact, the answer depends on the dimension. So if the dimension is even or is 3 mod 4, then length commensurability implies commensurability. Now in the remaining case, when D is 1 mod 4, there are counterexamples. So there are lengths commensurable that are not commensurable. But returning to your question, so we don't have examples for D1 mod 4 when two things are isospectral. That seems to be a difficult question. There are some other nice geometric consequences, so let me mention a couple. These are not direct consequences from the main theorem, but can be also used using the analysis of weak commensurability. For example, hyperbolic manifolds of different dimensions are not length commensurable. So really, if you look at the lengths of closed geodesics, you can figure out the dimension. And in fact, to show more that their length spectra are quite different in some very precise sense. Another thing is that the length spectrum distinguishes complex hyperbolic from real hyperbolic and quaternionic hyperbolic. And in these in these statements, you don't even need arithmetic. So the precise statements are given in my article. And finally, here's our contribution to the problem, can you hear the shape of a drum? Now, suppose we have two isospectral compact local arithmetic spaces. Okay? Then, if one space is arithmetically defined, so is the other. So previously we saw that the length spectrum can see if your manifold is arithmetically defined. It turns out that the Laplace spectrum can also see if the manifold is arithmetically defined. Next, they will have the same isometry group, even without assuming arithmeticity, so which means that the spaces will have the same universal cover. And finally, let's assume that one of the groups is arithmetic. Then if the type of G is different from one of those three exceptional types, then the manifolds are commensurable. So excluding these three inconvenient, let's say, types, we can say that indeed you can hear the shape of an arithmetically defined drum, at least up to commensurability. So I have shown you various geometric and even analytic results, but the point that needs to be made was that all of them were obtained by using purely geometric techniques, which probably justifies my giving this talk in this algebra section. So, and in the remaining 10 minutes, let me discuss the algebraic problems involved in the analysis of this sort of things. Now, the underlying algebraic problem has to do with understanding algebraic groups that have the same isomorphism or isogeny classes of maximal tori. So the precise connection between weak commensurability and this problem is a bit technical. It's described in my article. But the problem of understanding algebraic groups having the same isomorphism classes of maximal tori makes sense in its own right. Okay. Here is a formal definition. So suppose we have two absolutely almost simple algebraic groups, G1 and G2, defined over a field K. Now we say that they have the same isomorphism / isogeny classes of maximal tori. Obviously, if for every maximal tori, K torus of one of them, there exists a maximal torus in the other one, so that there exists a K-defined isomorphism or isogeny. That's self-explanatory. And vice versa, of course. Now, our analysis of weak commensurability gives a complete picture basically for groups defined over number fields. So the results are pretty much parallel, so I will not restate them. Again, there are three bed types, as before. And if the type is different from one of those, then a group is completely determined by the isomorphism classes of maximal tori. Now, for the bed types, there are counterexamples, but in each case, there are only finitely many possibilities for the other group once you fix the first. Now, in general, to analyze this notion, we gave the following definition. So, with G as before, we define the genus of G as a set of K isomorphism classes of K forms of G that have the same maximal tori as G. And in our work, we focus on the following two issues. First of all, when can one say that the genus reduces to one element? This means that in this situation, our group is completely determined by the isomorphism classes of maximal tori. And also, when can we say that the genus is finite? Now, what we did first was we looked at a similar problem, but stated in the situation of division algebras, where one can define the genus using maximal subfields instead of the corresponding maximal tori. So suppose we have two division algebras, D1 and D2. We say that they have the same maximal subfields, of course, if they have the same degree, n, and a field extension of degree n can be embedded into one algebra, even only if it can be embedded into the other. And then we define the genus of the algebra as a collection of Brauer classes that are represented by division algebras having the same maximal subfields as the given algebra. Now, class field theory, and in particular the theorem of Albert, Hasse, Brauer, and Noether, gives us quite good understanding of the genus over number fields. First of all, if we have a quaternion algebra, the genus always reduces to one element. So a quaternion algebra is completely determined by its maximal subfields. And for any algebra, the genus is finite. And now let me show you a couple of results that tell us what happens over fields more general than number fields. The first result is the following, which was obtained jointly with Vladimir Chernousov and Andrei Rapinchuk. So suppose the base field K is the field of rational functions, either over a number field or over a finite field. And suppose D is a central division algebra of exponent 2. Then the genus reduces to one element. There is some history behind this theorem. So when we wrote our paper with Gopal Prasad, nothing was known really along these lines. And we very cautiously asked the following question. Now take our field to be Q of x. Is the quaternion algebra over Q of x determined by its maximal subfield? So the affirmative answer was given by David Saltman, and then in the joint work with Skip Garibaldi, they handled the case of algebras over K of x, where K is a number field. Then subsequently, we proved a certain result which is called stability theorem, of which this is a consequence. Of course, to be of exponent 2 is a huge restriction, but the point is that you cannot go beyond that. So using the opposite algebra, it's easy to see that the genus can be trivial only if the exponent is 2. Okay. On the other hand, we have the following finiteness result. So suppose we have a central division algebra of any degree over a finitely generated field K. The assumption is that the characteristic is good, namely the characteristic doesn't divide the degree. Then one proves that the genus is finite. And again, let me remark that one cannot drop the assumption that the field is finitely generated. Namely, there is a construction proposed by various people, this list might be incomplete, that allows one to construct even quaternion algebras with non-trivial and even infinite genus over infinitely generated field. Now, both theories rely on analysis of ramification, namely the following result seems to be useful. So suppose we have a division algebra and a discrete relation of the center. Now, if D itself is unramified with respect to K, then every algebra in the genus is unramified at this place. So ultimately, the finiteness of the genus reduces to the finiteness of a certain unramified group. Now, I'm almost out of time, so what we're doing now is we're trying to generalize this to arbitrary algebraic groups. So in particular, it's natural to propose the following conjecture. Suppose we have an absolutely almost simple group over a finitely generated field of good characteristics. So for each type, there is a list of characteristics that are considered bad. But it's a finite list. Then we expect the genus to be finite. Now, this thing at this point is known for groups, of course, over number fields, and it's known for inner forms of type A n in general, and it's also known for some spinor groups conditionally. It depends on the finiteness results for unramified cohomology of mu2, so plus minus. So all this is described in my article, but there is one update. So conjecture 7.8 in the article is already a theorem. So basically what it says is that the set of places of bad reduction is determined by weak commensurability. Thank you very much.
Are there any questions? If there's no questions, we'll thank the speaker again.